Welcome back. So the second question in this series is which of these compounds that we see before us has a permanent dipole? So for A we have H2CS, B we have HCH3COCH3, and for C we have CH3, CH2, 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 CH3, right? So let's go ahead and drew these out ahead of time. That way I can go ahead and explain them. So what we're looking for is a permanent dipole. So we're looking for an imbalance in the electronegativity in the molecule. So let's look at our first contender, H2CS. Well, we can see that in the Lewis dot structure of the molecule, we sort of have a little bit more of a electron density around sulfur, but the electronegativity of sulfur isn't really all that much. Doesn't necessarily cancel out the electronegativity of the carbon and the two hydrogens over there. So I don't think it's going to be our we can mark this and say maybe it has a slight a little bit of a dipole. At least there's some more electrons around the sulfur than there is the rest of the molecule, but it's not very it's not going to be a dramatic dipole. But in contrast, let's look at this compound right here. So one of the most important things to remember was whenever you see a compound that includes an oxygen is very electronegative. Oxygen likes to hoard all the electrodensity of a molecule. It tends to do that. So this is going to have a permanent dipole in the direction of the oxygen. And if we look at our third option here, we see that it doesn't really necessarily have an imbalance. This is any dipole in this direction is perfectly mirrored with, or I should say, any electric field in this direction is sort of canceled by electric field in this direction. So this doesn't really have a dipole. So we're gonna say that the correct answer here is our CH3COCH3, and that is indeed the correct answer.